Hello, hello. Yes.
Aber nicht anbieten. Hast du überdehnt?
Good morning. Good morning and welcome to our symposium on integrated and safe motion for mobile robotics. It's a pleasure to see such a diverse and esteemed group of partners gathered here today to delve into this ever-evolving field. Throughout the day, we will have an exciting agenda planned. Can you please calm down, everybody, for a second? Good morning, everybody. Welcome to our symposium on integrated and safe motion for mobile robotics. It's really a pleasure to see such a diverse and esteemed group of partners gathered here today to delve into this ever-evolving field. Throughout the day, we have an insightful agenda planned, packed with insightful discussions, presentations, and demonstrations. Together, we will explore cutting-edge technologies shaping the future of safety in robotics. I encourage you all to actively participate, ask questions, and engage in meaningful dialogue throughout the day. Together, we can drive innovation, foster collaboration, and pave the way for a safer and more efficient future in mobile robotics. Once again, welcome to our symposium, and thank you for your valuable contributions to advancing the field of mobile robotics. Let's make today's event a success together. Thank you. We will be now hearing Igor Snitsky from Müller & Partner Company. He will tell us something how you can achieve safety compliance for AGV applications economically. You will have the opportunity to ask questions and make comments in a short 5 minutes to 10 minutes Q&A session afterwards. Thank you and have fun.
And Jan, thank you for the for this opportunity to be here and to tell you something about compliance with safety components. That's the topic that you see. How can I achieve compliance with a complex system, and what are the efforts of this way? I'm Igor Snitsky, and I'm a managing director from Müller & Partner, and also I'm a machine safety expert and occupational safety expert. So the first question of this topic is, what are the goals? And the answer is quite how could it be? You see there a list that for AGVs you see here a standard, and also for robots you see here a standard, and also you see some standards that are also important for achieving compliance in CE market. Yeah, we have here an example, a nice example, I think, and what are the, how I say, you have here a system that has all Type-C standard, and also we have for the robot and Type-C standard too. So that's the maintenance requirements for the whole system. So the next question is which subjects areas are important, and that's all activities over the whole machinery life. So that should be assessed, and therefore you need the protective measures, of course, and that you get over these topics that you can see here over this list. So intended use, reasonably foreseeably emissions should also be assessed. That's important. And of course, all the technologies and operating environment. And you see here that the safety measures are very in focus for CE mark. And we can see why. First of all, the safety measures includes 3 steps to achieve the compliance of your product. The first step is always inherent safe construction. So you need make measures that the hazard source are minimized or eliminated. And if there are not enough, then you should take the second part for the technical protective measures. And at least you should give use information or user information for using your product. So that's the concept, that's or the method that you apply, that you can apply the compliance of your product. And from the step 2, from the technical protective measures, we have some special one, the safety functions. And how you can imagine, that's our the mandatory safety concept for AGVs and also for robots that are not in a fence and will be used in a fenceless area. And therefore, we have a question that what are the safety functions by robots, for example? They are given 3 concepts to get the right safety functions, and you can see here. So we are here about corporate application. That means the system is fenceless, and everybody can go to the product and can get a collision or another hazard from the product. So therefore is from a standard 10 to 18 part 2 that you have seen before that are power and force limiting. And you get also another standards, and for example the AGVs also use the safe area protection, so that you have with laser scanner maybe. So that's are the concepts. And behind these concepts you have many functions that you need. So there should include in your product, and that makes it easier to get the application safe. And what is the effort to get the goals that we have seen? That is, that's sorry for that. That's a little bit error here. The efforts depends, of course, of the integration, safe integration in the product. If the product have no non-safety integration or non-safety functions, so that will be a lot difficult to get compliance. And you see the effort for the using these systems or for the achieve, of course, of compliance if you have non-integrated functions. Because you have an engineering part and you should all the functional safety requirements achieved. And what are the opportunity? The opportunity is that you use products or components that are all also integrated with functions. Maybe partly integrated with functions and you need only one or two safety functions that you developed self. But the best case is you have full integrated components. And what does it mean in time? So if you full integrate this products, it's a few months. You need, of course, apply the manufacturer informations and also apply the installation informations, and then you can get in the application, and then you achieve the compliance. But if you need an engineering or you full engineer a product or components, that take a lot of time. Yeah. So, and I look at the time. Yeah, that's the message that I have bring you here, and thank you for your attention. So, have anybody some questions?
Yeah, I have a question. For your knowledge, how many robots, AGV, are full compliant in the market right now?
What do you mean with food?
If you feel they are really full compliant or not, that is my concern. If there are so many in the market, I'm not sure if they are really fully comprehended for the safety.
Yes. Of course, there are some products that are not full completed in the safety concept and the safety functions. And the liability is by the integrator to use these components or to use these products. So be careful if you have not all safety functions that you need for your application, because if the happen and danger, then you get maybe some problems with a judge. Okay, another question? So I'm in time, 20 minutes.
Perfect.
Okay, thank you. Thank you, everybody.
Sorry, we have some problems with the equipment here. Apparently the lines keep going up and down. We don't have it really under control, but we are doing our best.
Das war alles.
Okay. So the next presentation we are going to hear will be Andrea Fehr from Synapticon, of course, and he will tell us something about safety in mobile robotics. Andrea, stage is yours.
You will need more time anyway.
Yeah. Can you hear me well? Yeah?
Yes.
Seems so. Okay, good. Then in 1 minute I will start. Okay, I don't know. Don't be too picky. No one outside. So yeah, my agenda for today, what I will be talking about. So what is functional safety and what it isn't? Of course, today we have a few people here who are way better experts in safety, and they will talk about safety after me. So I'm not going to leave it here. I'll just kind of, for myself and for everyone else, just remind what safety is and what it isn't from more like an engineer's perspective. And then I will talk about what we call the next generation AGV AMR system architecture. Then give a brief overview of the components, so the FSOE, safety over ecosystem. There has been many new developments
ideas here. And then present you the Synapticon reference solution. We have a robot in the back, which we how it works. Why do we show it? Yeah, so I like this citation from Wikipedia because it points out that the objective of functional safety is to ensure the freedom from unacceptable risk. And this doesn't mean that it completely removes the risk. And what is acceptable and not acceptable is defined by the norms and standards, luckily. So you don't have to decide for yourself what is risky and what not. The legislators, the European Union, so yeah, vehicles 100% safe. It's never 100, but you need to follow the norms to reduce the probability of a dangerous failure to an acceptable level. So what is an acceptable level? I'll not go into the norms. Probably someone else will talk about them. I just wanted to show we know about them. There is many of them, and they're important. The first few norms here in the list are important for us at Synapticon. They're important for drive systems, for control systems, how they work inside, and general machine directives. And then the last few in the list are important for vehicle builders, so it's for integrators and also vehicle designers. So on the bottom, I just reminded of the seal and PL levels. These are some diagrams showing the different seal levels. These safety levels are defined also by the norm, and they basically describe the probability or the reliability of the components. In the mobile robotics area, seal2 PLD is the level that usually is required. Our components, as identical in many other components from other vendors, usually have a higher reliability than required, namely seal3 PLE. The performance level itself is defined through based on the frequency of exposure to danger and the severity of the injury that can occur. Again, level D for mobile vehicles. I will not go into details, like I said. So there is a common confusion among engineers what functional safety does and what it does not. So industrial safety systems, also in robots, are designed to operate seamlessly in the background and only act if it is necessary to prevent an accident. So this means safety encoder, safety drives, safety PLC does never control the actual speed of the robot. It only monitors if the speed is at an acceptable level, and only if it's violated, then it finally stops the robot. So, yeah. So typically, functional safety does not control the speed; it only monitors. This is important. So I just generated a picture with the AI. Imagine this guy here, he's looking at the workers. He has a lot of buttons to press in case something goes wrong. And only if they do, something is going wrong in the factory, he reacts. That's our safety system, right? It doesn't actually have any control what's happening on the floor. It can only stop it. Yeah, but we also, of course, don't want to stop only. We want to drive. And yeah, we'll just briefly explain this concept in the example of speed monitoring. So we have a vehicle here that's running to, let's say, a relatively high speed, and there is an obstacle or human in front. And the safety system defines several zones with different speed limits. So further away we have a higher speed limit, and closer by a lower speed limit, and ultimately in the zone right in front of the vehicle, it is necessary to stop because the mass of the vehicle and its speed is dangerous and cannot be stopped fast enough. So it means if someone is in that zone, you can already assume the speed was limited below speed limit 2, and then the remaining stopping distance makes it necessary to actually stop. So when you enter the red zone, the vehicle must stop. So what does the safety system do here? In this moment, nothing, because human hasn't entered the zone. So now we're getting closer. And what we have here is the safety system is basically defining a speed limit for the first time, but it doesn't immediately enforce it. It gives some time to the control system to actually reduce the speed. So these speed limits are usually delayed by, let's say, 100 milliseconds. And the robot controller notices this because the safety controller, robot controller communicate, and then limits the speed, right, to the next level. So that's very important. So the safety system just informs the robot controller, okay, please limit the speed. I will wait 100 milliseconds for you. Okay, and we see we managed to limit the speed. We go further. Again, we're closer. We limit the speed to a lower level. And then ultimately, when we're too close, we expect the robot to have speed almost zero. And again, the speed limit is reduced to 0. Right? So what happens if the robot controller does not manage to control the speed within these limits that the safety system is prescribing? So in this case, let's say we are in speed limit zone 2, and the time delay has passed, but the speed hasn't been reduced. In this case, the safety system falls back to safe brake control and safe torque off. It means the motors are powered down and the brakes are engaged immediately without any delay. So this is the first time the safety system actually influences the behavior of the robot directly. So it means by hardware, it basically prevents the drive system to move anywhere. So yeah, these functions and these kind of approaches, this is a relatively limited, simple approach. Vehicle driving only forwards. Of course, you can have vehicles driving sideways, backwards. So you have many of these zones, and the number of speed limit zones is defined by the user. So we can have up to, some of the systems support up to 100 or more than 100 individual zones that can be defined in all shapes and sizes. So I mentioned before next generation AGV AMR platform. Why do we need a next generation? Mostly we need new things when we want to get more cost effective, more performant, more simple, more reliable. Right? So here it is. This is the traditional architecture of a vehicle. We have an industrial PC inside, usually used for the entire vehicle control, navigation. And then we have a safety CPU. This is necessary to control the speeds and control work with the scanners and coordinate the entire safety in the vehicle. And then this safety CPU usually needs a lot of safe IOs and interfaces to connect to encoders, to drives, to trigger the safety functions inside of the drive with the cable. We have open communication. Then we have laser scanners, and these laser scanners are also communicating with the safety CPU. All in all, I didn't count the number of cables and wires here, but it's a lot. It's maybe 12 cables. We have only 2 axes. This is a vehicle with only 2 drives. The robot we are having in the back, it has actually 4 drives. So in our case, we will need a double the amount, 24 cables, to achieve driving and safety. And this doesn't take into account the power supply cables. I forgot to put them. So yeah, it is a nightmare to assemble, produce, wire, and maintain. But this has been working pretty well for many years. But today vehicles need to be lower cost. The number of vehicles that we build are way higher. So what do we do? So you may be familiar with our products. I'll not talk about our products in this presentation, but we have combined the safety encoder, the motor encoder, brake, some safety functions, and a servo drive in a single unit, and made it in a shape and size that you can put it inside of your motor and gear. So see here, the drive, the safety encoder, the brake motor and gear can now be combined. So we end up with this kind of architecture. So count the cables here. We have a total of 2 cables for the drive system. So actually only one Ethercat bus. And all the functionality is pretty much the same like before, even maybe more advanced and flexible, because now for every zone that the scanner has, you just have it in your communication, right? For every new safety information you have, you have an additional cable to trigger the additional function of the drive. Everything is digital, true Ethercat, and requires a single bus cable to connect all the devices. And more importantly, if the vehicle, the number of drives grows, let's say to 4, 5, 6, for example, lifting something, you can imagine a vehicle that not only drives but also lifts, you just have one more drive. So the advantages of this, some of them are obvious, but I will just repeat: reduce cost and complexity, better diagnostics, reduce maintenance, and reduce engineering efforts. And everything is based on safety over Ethercat. I didn't talk about this, but safety over Ethercat is a sub-protocol of Ethercat. Ethercat is very popular in motion control applications, especially industrial robotics. Large companies like KUKA use only Ethercat within all of their devices, all of their robots. But Ethercat is not yet like the standard in mobile robotics. Mobile robotics is today still hanging onto the old school CAN bus communication. But Ethercat is a very fast growing standard. It's maybe worldwide becoming the most important standard for any kind of drive technology. So, overview of components. Of course, now this is all fine, nice, new technology. Can I buy the components? Is there a wide choice of components? I will not mention our direct competitors, but there are some, and this is very important to know. We are not the only company making servo drives with FSOE. There are also some competitors making also compact low voltage drive technology with this kind of functionality. But we are offering 2 product lines. One is the Somonet Circle, and one is the Somonet Integro, which we introduced last year. But the FSOE communication will be available in 2026. Actually, sorry, not samples is wrong. Samples will be available in 2025. FSOE will be available in 2026. So, and for the integrated drive systems, you can check out some of our exhibitors. We have direct drives, drives with gears, here integrated with the Circular series, using our integrated safety feedback and FSOE. Now, one of the most expensive, most important components of the safety system is the scanner, and we are pleased that SICK has made the first step a few years ago to introduce the Microscan 3 with Ethercat. And actually, to be honest, without this component, we wouldn't have entered the mobile robot market with our product. This was the key, to have at least one scanner on the market that can enable this elegant architecture. But meantime, there is also other vendors who have introduced the scanner recently, so that's of course great to not have a single source here, and more are to come. So I'm pretty certain that this will become a very common technology in scanners. For the safety controllers, there we are luckier. There we have a lot of controllers on the market, and I have just listed some brands and some solutions that we have been working with at Synapticon. So back of this, of course, Immerse, and they have a lot of safety technology. They're very simple and small and widely available. And then we have some more specialized solutions that are more powerful, more flexible, from some of our partners and other brands. And important message here is Synapticon is going to work with all of these partners and these components to integrate reference architectures. Why do we do that? We want to help our customers implement their AGV. So our engineering and our application engineering will implement complete solutions based on these components for our customers in the future. And my last slide is the robot in the back. You have seen maybe when you entered. was implemented recently. This is basically the first example of the Synapticon reference solution that we provide to our customers. This is now, in this case, based on the back of safety PLC, a simple one, a microscan tree from SIG, using 4 times the 7 safe motion, and a motor cortex motion controller to realize the remote control via space mouse and control the robot kinematics. So what does the safety PLC do here? It computes the directional omni-wheel kinematics, forward kinematics, speed of the vehicle in X and Y dimensions. So it's a 2D speed of the vehicle. It was all done with few multiplications and additions. So it turned out to be much simpler than we thought. And very important, it switches the protection zones of the scanner. So depending where the vehicle is, to the left or to the right, it starts monitoring the zones on the left or the right. So basically the safety PLC is the brain of the safety application, and it's programmed with standard PLC type programming using functional blocks. Yeah. The safety scanner monitors, I put X because I don't know how many zones we have, but this is variable. There are many protection zones. There are probably many levels. We have only one scanner here, so we are allowed to only drive forwards and left and right, because we didn't have time to put the second scanner. But it's possible, of course. And then our drives that provide safe velocity information through this FSOD bus, acting as a safety encoder, and that ultimately will stop the system in case a violation of speed happens. So I invite you to join me in the back to talk about this reference solution data. And I think this has been the last slide of my presentation. So yeah, thank you very much.
I'm amazed, Andrea.
Yeah. So we have some time.
Right on time.
Right on time. Okay, so I guess we can answer some questions.
I have a question regarding what was the biggest challenge in the safety development for circular?
In the safety level?
No, in the safety certification.
Biggest challenge in the safety certification. Yeah, so it started with that first the conversation with the TÜV was maybe 5 years ago, and we said, okay, look, we're going to use these our own encoders that we make with dual channel with two encoder chips that are not safety chips, and TÜV said, why don't you just not use standard safety encoders? This is state of the art. And then we were arguing that in robotics we don't have enough space for these safety encoders as they are, and they're costly. And then TÜV, they went home after this conversation, thinking about it, and a few weeks later we got the feedback from TÜV. Not only it is going to work, it's going to be safer than any other safety system, and we were surprised. So it was a fear we had, but it turned out to be easy to solve because of the competency inside of TÜV. Their very deep understanding of electronics and how they work. So this was the first kind of fear we had, that we will just be declined. But then it's just tedious work over many years, like documentation, validation.
Factory inspections.
Factory inspections.
Like how many iterations did you have?
How many iterations?
Yeah.
So I think we didn't have really an iteration on the safe motion. We did start actually the project with a partner company, and then we canceled it after 1 year because it turned out that the microprocessors we had been using were too inefficient, too slow, and it was quite a waste of time and money. So I think we wasted maybe around 2 years in the beginning working with the wrong partner. Then we stopped, and then next time we went through without any iterations. So careful planning, writing specification. I think I wrote the specifications for 3 years before we actually started working on the product. That's, I think, the thing. And then it went through. And it delayed itself, of course, but there was no iterations on this.
question. When you do multi-axis control, like in your reference implementation, then the system also has to have some knowledge about kinematics. As you say, when I drive in one direction, I need to protect the fields on that side. So what I would be interested in, where in your system is this actually stored, this information, and how flexible is it actually? How can you change, or how complex can such a kinematics be, also considering that everything still has to be computed in the same way?
That's a very good question. And yes, I was wondering myself how to do this. We were assuming that controllers can compute such kinematics. And it turns out we were right. Actually, even the backup safety PLC, which was made for general automation applications, is capable to compute the kinematics of this omnidirectional platform. I'm not certain that this is the most complex kinematics. There's probably other kinematics. We are intending to implement all common kinematics on the backup platform, but then we will move on and do it also with other platforms, which are more capable than backup. So we started basically with the, I don't say least capable platform. Backup has multiplication, division, for example, is important, and it can handle, let's say, analog values. So let's say you can read the speeds in their native resolution from the drives, and then scale them, and then multiply and divide with certain values. So if you compute forward kinematics, is way easier than inverse kinematics. Yeah. So we discretized the formula, and from having a complex matrix down to a simple discretized formula. So for the Omni wheels, it worked. I'm curious to see if there is some limitation with this backup. But then we have other safety CPUs, for example, BBH. They have even sine, cosine, tangents functions, so we can do multi-axis robot arms, for example, with this. So certainly we can do AGV or AMR. More questions? No? I guess I was very clear about everything. Absolutely. Thank you very much.
So the next presentation we are going to hear is from Lena Bitzek from TÜV Süd, and we are about to start in roughly 10 minutes. Okay? Thank you.
morning, everybody. Next presentation by Jan Feld from SIP. And I think everybody over here should notice SIP. Like, we exist in over more than 150 years with 26,000 employees, including 15,000 technical experts. And SIP prides itself being 100% independent and impartial. And we are located in more than 1,000 locations worldwide, as you can see here, in different countries. And one or two sentences to my person. My name is Lena Bitzek. I'm working as a test engineer in the team Smart Automation for SIP. And I'm working there almost 1 year right now in the topics on AGV and robotics. And if you should have any questions, don't hesitate to write an email afterwards or to go to our place here, just in front of the door. And we are located in Munich, and I'm working for TÜV Product Service. And TÜV Product Service has 3 divisions. One of those is consumer product services, like household appliances, sport equipment, and stuff like that. Then we have MHS, like medical and health services. They're doing active medical devices, non-active medical devices, and also vitro diagnostics and the stuff you can find in a hospital. And then last but not least, we have commercial product services, transportation, advanced manufacturing, and industrial and energy products. There you can find also the team Smart Automation, the team I'm working in. And today we are going a bit into the topics of our team. Then we will give a very superficial overview about the EN ISO 3691/4. And I will give you an overview about the general testing process. Then what is the team doing? We are doing various testing of robots. There we have industrial robots, like you see on the first one. Then we also have cobots and robots, like maybe the ones you know from a restaurant delivering the food. Then we also have the applications. We are also doing industrial 3D printers, automatic doors and gates, and of course also AMR and AGVs. And also part of the systems are batteries, chargers, drives, controls, and also high-level functions. And yeah, we have various types of robotics. One of those is the industrial 3D printer, not 3D printer, industrial robots, and they are automatically controlled, reprogrammable, and they could have 3 or more axes, and they can either be fixed or mobile. Then we also have the cobots, like collaborative robots, and a short cobot. And they refer to an industrial robot, but they are within the same safeguarded space. People, as the operator and also the robot, are working together. And then we also have mobile robots. They are battery operated, and there could be a mobile platform with or without payload for lifting and carrying or product picking. And of course, they also need a lot of safety requirements, and we are going a bit deeper into the one from AGVs and mobile robots. There first you have to check where you want to sell your product and which market you want to go, international, Europe, or North America. And then you have all of the different laws and guidelines and safety standards. And today, as I said, we're going a bit more into the ISO 6391/4. And yeah, in Europe, we are using the 3691/4 for driverless industrial trucks and their systems, and also the EN 1175 for safety in industrial trucks. And for America, it would be the UL 3100 for automated platforms, which is the convert to the 1175. And then we also have the Ancilia R1508, which is similar to the safety requirements of the 3691/4. And both of those have different safety requirements. There we have the mechanical ones, electrical ones, outer environment, and also EMC. Then we have also a separate testing laboratory in Schraubing, and also of course functional safety, as we heard in the two presentations before. And then where does the ISO 36914 comes from? It has its roots in the EN 1525 and also in the EN 1526. And the latest version is quite new, the EN ISO 3691/4 from 2023. And then here you have a quick overview what's in the scope of the 3691/4. There we have like the AGVs, mobile platforms, conveyors. All the pictures you see are in the scope. And then if you want to know if maybe your product also is in the scope, we start here. And the first question you have to ask is, whether an industrial application? No, then it's not in the scope. Then if it's yes, then we're going to ask, okay, mobile platform? No, then we are going to general machinery standards. And when it's yes, then we are going to ask, okay, is it navigated autonomous or guided? When it's guided, we are going with the AGV, automated guided vehicle. And if it's not guided, if it's autonomous, then we have the AMR. And both of them are in the scope of the ISO 3691/4. And then we have the AGV and the AMR. They're examples. On the left, you can see the autonomous mobile robot with those sensors and powerful onboarding computers able to understand the environment, and it can plan its path without routes. Then we also have the AGV on the right, and this follows fixed routes, usually along wires or magnets in the ground. You can see here on the ground the magnets. And both of them have different stability, load handling, and all of those have to be tested. And one function that has to be tested is the detection of persons. And there we are testing it. I just picked those as example. We are testing there with two cylinders, a bigger one you can see on the left, and a smaller one on the right. And then you have to put it in front of the AGV. And normally the AGV should stop before it hits the cylinder. Or if the AGV has a bumper, then it hits the cylinder, but there are different numbers of Newton where it doesn't exceed, but it's not allowed to exceed. And just to make sure that nobody gets hurt to the AGV. And then we have to test it in various positions. As you can see, this is the table out of the norm. And we also are testing with one mirror. And in the end, you can see, okay, I tested there, and it stopped everywhere. Then you can write pass. Otherwise, it would be failed, but in the end, there should stand everywhere pass. Otherwise, the test is failed, and then you have to change something in your AGV. And then the general testing process, there we have 5 rounds. And you also can do only the development support without certification and without testing. And maybe let's say, okay, we will need 10 hours because you don't know how to do your risk assessment or how to create the documents you need. And then it's like a ping pong. At first you give us the input, like the documents or information about the product, like the definition where you want to go with, which is the target market. Then we also need a description of your product, because we're not that deep inside your product like you are. And risk assessment, and then we are going to check the documents, if everything looks good, or if all the functions we need are inside the documents. Then on the next, we are creating a test plan together, and we are checking your installation concept and the circuit diagrams. And yeah, this phase can be really short, or if the documents are not finished yet, or if we have to change something, or you have to change something, then it could also take some weeks or maybe also a month, depends on you. Then we have the testing with a prototype, when it's written maybe in your manual. We also need the visual testing, because if you have written in your manual, okay, we have various warning labels on the product, then it's fine when it's standing in the manual, but we also have to check that it's also on the AGV, that you did everything like you brought us in the documents. Then also we have to do the electrical testing and have to check if the safety functions are working. And for those, normally we need 1 prototype or maybe 2. And then maybe we have to do some more tests like EMC testing separate, and then we put everything together and write a technical report. And at the end, you get the certification if everything is passed. And yeah, that's a quick overview how the process is going. That's it. Thank you for your attention. If you have any questions, you can ask them right now, or also
The standard is mentioned about the slope of the surface material.
the surface material of the AGV or the product, or what do you mean?
In testing. There is a flat surface, you show some pictures. What about
Yeah, you know what you mean.
What
This one?
about if there is a slope, we must hit the slope? It's not a flat.
And for this test?
Yeah.
No, there's also a different test, like a RAM test, maybe you mean?
Yeah,
But it depends what is your maximum, because normally the ground is not everywhere like flat, and then you have to test, okay, maybe there's a 1 or 2% it's not planned, and then you have to test is it also working if you have a 1 or 2 or maybe 3% angle, then you have to do the ramp test. And normally, I think.
That's also surface material. If it is painted or
Normally, I think I'm not quite sure. I have to check it in the standard, but I think normally we are testing with 3%. But if you in your manual is written, okay, the AGV is also working with 5%, then of course we are not testing with 3, we are testing with 1. But the test you have to do always, also when you're at ground floor. But it's not this one. I thought you were talking about something different.
I think he was asking about the surface. Is it
Yeah.
painted, or is es lackiert, der Boden, oder ist Beton, oder ist es egal?
No. You are asking this, what she said? Sorry, okay. No, the surface doesn't matter. We can test it at our side, we can test it at your size. It's the ground you have there.
You mentioned that the 3691 is for industrial applications.
Mm-hmm.
How about if the autonomous robot is operating in public environment like a restaurant? Is there the same standard applicable, or?
There, I'm not right sure, but we can check it in the end of the presentation and stuff.
Regarding the differentiation between AGV and AMR, so does it have to be a physical guiding system like a rail, like you mentioned, or if I have like a virtual line follow, does that make it an AMR, or would that still be guided vehicle, so to say?
What do you mean with virtual?
Like you have a robot that localizes, you draw a virtual line that only follows that line without evasion, let's say. Is it then an AMR already, or where would that fall in which category?
I think it's not an AGV then, but I'm not 100% sure.
Thanks.
So when you have to do these tests, assuming you're using the SIG glider sensor, then you don't have to do this for some person.
No, you're always doing the test, but maybe it's not built right inside. You have to check that it's working, and before you get the certification, you're always doing the test. Maybe sometimes you also have to check the components if they're already certified, and maybe if you want to go to America, then you're checking, okay, are they UL certified? And when you have certified components, it's easier for us, but we have to do the testing. But when they are not certified, then we are testing the components separately. If something could be damaged through those components, and if they are passing the test, then it's okay if we are using those, but we have to do the test always.
To get your 2C stamp, or not just for this stamp, otherwise you don't need to test it, assuming you're sure you're meeting the requirements.
Yeah.
You mentioned electrical and insulation testing. Can you say a few words how this is done and what is it about?
It's maybe you have the you have to make sure that you have the right spaces between the components. We are testing with the high potential tests, especially for those that maybe when you put a high voltage, then the components are not working together when they have to.
And you're assuming...
In German it would be Luftbetriebssteigen.
Okay. But assuming that the voltage is maybe 60 volts?
It depends on the voltage you have written on your nameplate, and then depends on the norm. Normally it tries the voltage written there plus.
And if you're below 60 volt with the safety extra low voltage, then you still need to do the clearance and they're not, right? But this is, I think most vehicles are driving with 48 volt or below 60 volt. So these tests apply to trucks or vehicles with higher voltage, yeah? Okay, thank you.
It's also always like this, okay, we see what product we have, what is inside, and then we are playing together with you which tests do we have to do, then you can prepare them and check, okay, we're doing those tests when you come to our place.
I have a question. If you have done the test and you have the certification and then you use the same components to build a similar AGV or AMR?
With the test, we wrote all components down on a list, and if you maybe sometimes you want to use something else, then we can add maybe almost the same product for another company, but you have to use always the same components like we have tested a little bit.
But then you don't need to repeat for every.
Yeah, there are different certifications, and if you're only doing a limited production certification, then you maybe say, okay, I have 10 products, I only wanted to test those 10, then we check all of them, or you want to certify the whole product, then it's only once, and then you have to build it the same. I think that's it.
Thank you. So now we're going to have a lunch break. The next speech will be Philip, I guess, after the lunch break at 1 p.m. There are cold foods in the fridge, cold drinks in the fridge, so warm drinks outside, and the dinner will be also served outside, so enjoy your meal.
Dinner, you mean lunch?
Lunch. Did I say dinner?
Yeah.
No, lunch.
It's the cold lunch. No.
Dinner haben wir nicht. Warm. Und alles auch. Maybe that's another we see us there now. Maybe now we will discuss
And then I said it again.
But in Europe, theoretically, hey, no,
Think about it, and you will have a very, very well-functioning game.
So I cannot really tell the customer
Ja, ich habe gerade einen. Das ist die Variante, wo dann Break und Sensoren von der Synapticon entsteht. Da war halt das Problem, dass wir eine Bremsbelastung oder Belastung und das war natürlich nur gewesen. Das ist 10 Minuten wieder, ja. 10 Minuten wieder, dann nicht mehr gemacht. Jetzt ist es 5 Minuten wieder. Ich habe viel Bremse, also ich kann heute auch 40 Minuten. Aber es ist halt wahnsinnig, das auch weiter. Das war dann schon die Beratungstechnik, ja. Ich würde gerne mal diese Kabel, die dann Box geht. Da haben wir schon gesagt, Lagen. Ja. In dem Sinne ist es halt ein Kabel, die man anschaut. Also nicht viel drin, ja. Und die Wellen werden schon so.
Habt ihr dann da quasi Spezifikation, dass wie viel
So ein Last, ja. Hier drin ist jetzt nicht unbedingt.
Ja.
Hier drin ist auch irgendwas. Also das jetzt hier hat radiale Achsenlast. Variante beziehungsweise das ist eine Vorgängervariante, da haben wir dann eben nicht 2 Sicherheitssensoren drin, das ist zwei Sensoren, sind aber natürlich die Bremse. Rein so geht. Und das andere ist jetzt gar nicht drin in diesem Aktien. Oder einfach auf der Webseite. Es kommt jetzt ein Frontschirm zum Beispiel. Momentan noch anderes Winkel gewählt, aber steht nicht für die Mutter. Und dann hast du sozusagen einen anderen Steuerfarben. Und dann kannst du halt den Schirm auch so drauf. Das ist halt etwas größer. Jetzt so eben ein kleines AGV, das Unternehmen. Und da haben wir jetzt so vielleicht bis 98 einfach mal die Technik kennenzulernen. Es ging alle viel. Also, Milchtechnik, ja. Wegen Alu haben zusammengeschraubt. Aber im ersten Kurse halt funktioniert. Da muss man sozusagen seine erste Konzentration zusammenmachen. Ja, so.
tatsächlich die aber tatsächlich auch machbar in einigen schönes Lernen, aber zur Qualifizierung halt vor allem nochmal die Bautechnik, aber im Endeffekt
was man nicht fällt, abhört in der Video, oder was man nicht gebaut hat.
aber auf jeden Fall bis zur Das ist so ein bisschen das einzige Szenario. Ja, aber ich mache das mit dem Erfolg. Übergabe oder der tatsächlich ist auch mal
selber viel programmieren oder?
Ja. Ja, beides.
Wobei ich muss sagen,
ich habe tatsächlich mit AGV die letzte Zeit Arbeit verwendet. Es ist sehr gut, mal so ein erstes Tool zu haben, was noch nicht geht. Ich habe so eine kleine Quick gemacht letztes Jahr. Da bevor ich aber nur angefangen habe. Einer meiner Player auch noch so 3 Buttons, aber wollte ich nach wie vor und habe dann hat er aber alles gemacht. Ich muss da schon entweder sehr, sehr spezifisch die Eingaben machen oder das ist nur so ein bisschen die Anforderungen erweitert.
ja, man muss dann aber ewig wissen, was dem Ding dann beibringt. Wie du das schreibst, das ist schon richtig gut sein. Ja.
Hallo! Los! Genau. Wunderbar. Okay. Echt? Okay, ja. Ja, wenn wir morgen eben aufbauen müssen, ja, was man hier auch immer bilden können. Jeder kann nur den Motor naja. Nee, also das ist schon, ich sage jetzt mal, die Motoren, das ist was die Mechanikseite her dann beeinflussen können, ja, oder Schulen entwickeln, aber in dem elektrotechnischen Bereich Und der SPS bis jetzt haben wir auch nicht viel wirklich Neues gemacht. Also und dann macht das so aus, wie es jetzt ist. So, Stand, Logmatik. Okay. Weil ich sagen muss, das ist man noch nicht auf so einem
Ja, die Woche, gar nicht wie wir uns dann die Serien vorstellen wollen. Naja. Das ist Standard nicht mehr wahr. Wer ist heute sein größtes Problem? Aber wenn es anders studiert wird, das wird wenn es kleine Pizza sind, irgendwie hier okay, aber es war kleine Informationen zu müssen. Nächste Woche kommt das nächste und sagt, ich möchte sogar wieder. Ja gut, sowas wäre einfach zu machen, ja, aber wenn es auf Aufrichten geht, wenn es nicht auf Texte geht, dann, keine Ahnung, dann wird es schon spannend. Und komischerweise, wie man so spannend ist. Also bei uns zumindest in unserer Kunden merkt immer alles, okay. Hier haben wir so ungefähr eine Blick, aber halt.
Ja, ich sag mal, von der Größe.
Also unsere Kunden machen teilweise. Also die wildesten Sachen. Schon sehr über das bis hin Federn und was es gibt irgendwie. Deswegen für uns Motor, mach was drin. Schauen wir weiter. Ja, klar. Kunde ist schwierig. Kunde möchte natürlich gestern stellen und vorgestellt wieder. Hallo? Okay. Ich bin jetzt seit einem Monat aufgestiegen. Jetzt mittlerweile Geschäftsführer. Entwicklungsleiter gewesen, Spezial. Aber bei uns ist natürlich so, dass die Technik optimieren muss und darf. Ja, SPS das ist auf jeden Fall. Ich sage jetzt mal klein, gemütliche Ecke, wie so schon. In einem großen wobei da jetzt wir haben den Vorteil, dass wir in Deutschland produzieren. Das ganze Schiff halt zukommen lassen sozusagen, sondern können wir kurz, komm, mal, ändern uns. Aber mal gucken, wie lange es geht. Technisch gesehen sind die da drüben gerecht schnell. Ja, also da haben wir auch immer gut ausgestellt, sag ich jetzt mal, wenn wir viele neue Arme über den Fräsen. Rollen, Drehen, Zahn. Meinst du Motorantrieb oder meinst du die ist ungefähr Durchmesser 1, sag ich jetzt mal. Nee, das ist immer Spaß. Also ich bin kleine Rolle, wo ein größeres Unternehmen im Lager steht. Also ein Außenläufer wird aber jetzt nicht als normaler Roller, sondern als kleines Röllchen, um was zu tun. Prinzipiell haben wir zwei Unterschiede, die untereinander sind, aber die kann man nicht so wirklich. Ist eigentlich die kleinste, hier also die schmalste. Schauen wir jetzt momentan, wo wir drei Verkäufer haben, den drei Reiter, und für verschiedene andere Kunden haben wir dürfen noch keine Werbung machen, weil der Kunde Teile davon für die Entwicklung bezahlt hat. Dauer macht er jetzt circa 3, schätze ich. Und macht er gleich also weil die Überlastung nicht gut ist. Der macht jetzt 34. Ist natürlich so, dass wir jetzt machen können, aber dann passen wir Ansätze und ja, immer wenn es Zielspiel, dann können wir auch den Strom ausgeben.
Gut, auch von alles geklappt. Genau, schon.
Aber noch keine gute Serie. Ganz weit weg ist einfach nur 10
Ja.
Ja. Es ist einfach zu integrierendes System. Jeder Unterhol ist anders.
Was heißt einiges? Das ist halt einmal die Kamera würde ich schon wieder kalibrieren. Und müssen halt die Fälligteile wahrscheinlich einmal neu testen. Das ist schon sauber machen, weil ja auch dann von den eingestellt werden. Ich denke mal auch. Ja. Ich habe zumindest die Möglichkeit, wir haben ja auch war der Eingang kaputt und der andere drauf. Man kann es natürlich versuchen, aber die Chance
wir machen es ganz so, dass wir teilweise die Antriebe dann wirklich halt mit den Systemen
das sollte nee, schon mit dabei.
ein bisschen vor uns.
Das sollte eigentlich.
Von 1 bis beim BNC-Bereich so in Richtung 5.000 bis 15.000 Teile pro Jahr. Und im Bereich bis
genau, also Einsatz sollte passen. Ich meine, man muss ja
also bei den Großen jetzt eher weniger, aber bei den Kleinen waren es aber eben das.
Ja, klar. Dann viel Spaß. Lass uns da mal.
Was man halt hier sieht, und das ist ein schönes Beispiel, man hat keinerlei Probleme, Okay. Ja, man hat dann in der Vorstellung noch nein, das ist jetzt so Serienvorstellung. Dann haben wir auch DSLs, dann sagen wir schon mal, wir haben noch einen Meter. Relativ schnell an so Größen. Das ist auch nichts weniger. Ja, aber okay. Ja, das geht ja früher. Achso, Aber wir haben ganz wenig. Die anderen müssen das wirklich. Ich habe gesagt, was? Wir haben zwar natürlich ja, kann man so sagen. Alles klar. Schöne Wiedergabe. Nee, nur was gemacht.
В основном какие-то наш циркуль спрятали и без колеса.
Philipp? Ein. Unser Motor.
Da müssen wir einfach was machen.
Really? Can you tell the people?
You are the moderator. I cannot, you know.
Just in case you are hungry, there is more food at the moment being served. Make some noise. Mobile Robots Die haben halt zwei Westen. Da läuft es mit der SPS.
You're getting a louder voice.
Yeah.
Sorry. On the back pocket, is it working fine? Go ahead. Oh, yes, So that means when we get the space, that's the very checks and also they can adjust they really make them so this could be also based on
But it's also depends.
It works. Hello.
Gonna need another 5 minutes. Check the audio.
Ja, genau, genau.
Try. Yeah, now it's loud. It's louder than before. I think so.
Do you want louder?
Can you do it louder?
Yes.
More. Jetzt haben sie das Mischpult angebracht. Aber das hat gar nichts damit zu tun. Das ist das alte System. Das war ja nicht gleich. Eins, zwei, ja, ist gut. Danke. Okay, obviously it was like 2 minutes, not 5. So now we are continuing on our schedule. The next presentation is from Philipp Bjertkiewicz, and we will hear something about the evolving requirements of motion control software and mobile robots.
I hope you all enjoyed your lunch. My name is Philipp Bjertkiewicz. I'm the founder and CEO of the company in the Netherlands called Actioneer. We've been a long-term partner of Synapticon. We've joined Synapticon in our mutual efforts to create better motion control from the beginning, so 10 years ago, approximately. And today I will show you a little bit about motion software and software that you need for AGVs, but robots in general. So let's take a little bit of a look into the history of mobile robotics. It started with relatively simple devices or robots where we had fixed routes, we had relatively low speed, we had simple safety. So there's on this vehicle you see there's a bumper in the front. So if you're in the front and you hit the bumper, then it will automatically stop. And we had limited additional functions. Yeah, this development started in let's say the 80s of the last century. And of course, during time, we want more and more and more functionality of these kind of robots. And here you see a project that we also jointly worked on together with Synapticon. And it illustrates that we are moving from AGVs, autonomously guided vehicles, to autonomous mobile robots. So we have more access We have localization and navigation becomes more flexible, so we don't have wires in the ground anymore, but we use SLAM, so we scan our environment, we find our way autonomously. We also want to move faster and more accurate. Faster, of course, because that's good for our business case. The faster we go from A to B, the more work we can get done. But this also means that faster moving robots are more dangerous, of course, obviously. We want additional sensors, not only vision, but also sensors like LiDARs to scan the environment, to make a map automatically. And we want also access to data, because with the data of the robot, we can actually optimize the whole process of the logistics problem. Or maybe we can use the data to evaluate the status of our machines. So is there any problem going to happen in the future? Can we predict failures? And of course, we also want advanced more functional safety. Andrea Veer already discussed this, that we want to go from like digital safety, from on-off, it's either safe or not safe, to some kind of analog safety where you have a gradation of safety, where it's also like going to get dangerous pretty soon. So we have this orange level instead of green and red, we have something in the middle. And this also adds to the complexity, and also we need to solve this in software to be able to optimize all this. So these are kind of functional requirements that that add complexity to a mobile robot or any technology. But also we want for the OEMs that are these robots, we also want have some requirements, like we want modular design, so we can change for our client the layout of the same components in a different way for different applications. We also want less hardware dependency. So we saw that after the pandemic, a lot of hardware was unavailable, especially safety PLCs were very hard to get. And if you don't have access to the hardware, you cannot deliver to your clients. So you should be trying to have parts that are replaceable by other parts. And by using, for instance, EtherCAD, there are so many vendors now that support with IOs. You kind of can choose which vendor you want in case your preferred vendor cannot supply. And also we want an open platform. That means that we can extend the capability in the future. And we can create more ideas. So we are not limited by the platform itself, but that's one of the things we discovered when we started our company, is that's why we developed our own software platform, is that the systems that we could buy were not providing enough freedom. And then we had to take the decision, do we stay within this environment that we could buy, or develop this ourselves. So we decided to become the experts in an open platform that our users can then extend. And there will be many, many more requirements. So I didn't come up with this myself. So for instance, there's a Boston Consultancy Group did some research or made a model about how complexity of software grows. And they did that for automotive industry, and it is kind of analog to other industries. They also did it for the aerospace industry, but this also applies, of course, to mobile robotics. They thought that in the car business, so car manufacturing, they thought that electrification would simplify things. And it partially is true, you have less components, but the requirements of these components are becoming higher and higher. So that means we have extra safety standards. So maybe a bonnet of a car in the 1980s, this should just be like a cover over the engine. But now it has to be streamlined, it has to be lightweight, it has to be watertight, it has to be, it has to have all kind of maybe environmentally friendly paint. So more and more requirements come to the hardware as well. And these requirements on the hardware, they grow like n squared. So if you say that n is the number of requirements that you have, the complexity of your design is n squared. Follows this curve.
But if you look at software, it's a completely different thing. So there we have more like a trend of 2 to the power of n. So for every function, you add another power to the complexity of your system. So having more requirements means exponentially growth of your, for instance, they could measure it by counting the lines of code that goes into a car. And they see that this follows this 2 to the power of n model. So Boston Consultancy Group also thought about, okay, but what can we do about it? What can we advise to our clients, which are then the automotive manufacturers? And the way the solution that they came up with was like, think in terms of creating platforms. So you kind of compartmentalize your solutions, so or your problems basically. So you have a safety system, you have an audio system, you have the chassis, and all of these compartmentalized problems you solve with dedicated teams. And you just make sure that the interfaces are well defined and standardized maybe even. And in this way, you can kind of scale with the complexity. If you want to do everything by yourself, it's very hard to scale. Your teams get bigger and bigger and bigger. You get more and more specialists, specialists about safety of software, EMC, and this also happens in the mobile robotics world. So the solution is that you should rely on a platform or a number of platforms that solve your problems. So this is what we also try to provide for our clients. So we make motion software, and we also modularized our solution. So this is what a no-code solution for AGVs or robots in general. We saw that a lot of our motion control problems always required a custom solution. So we became very good at compartmentalizing these functions into modules that you can turn on and off. So this is a schematic of our software architecture, where on the left you see input modules. So this is where signals come from the outside or from the user. And then in the middle we have application modules. So it depends on the machine, what it is. So is it a mobile control, mobile platform? Then we need a mobile control module and a mobile logic module. Is it a manipulator, like a robot arm? Then we also need a manipulator module, which we could also have 2 robot arms on one vehicle. And then we have something called machine control, which is kind of generic. So everything that does not fit, everything that actually has very simple kinematics, we call a machine, like a gripper or some kind of actuator on your AGV. And this is handled by the machine control module. And on the right we have what we call then access control. And access control is actually can do server control of your access. So it's multi-variable access control. So this is how we complement what actually Synapticon is providing to you. Synapticon is very good at single access control. And we make this as a multi-access control layer on top of it. And on the far right, you see the connection to the field bus. So there we connect to Ethercat, and there you will find the Synapticon Circular and nodes, and also safety devices like SICK and Kuyo scanners. So with this application, which is actually one app, and we deploy this app to our client's hardware, so computer, and then you connect your devices to it. With this one app, we can already configure it, so without writing any line of code, to perform different tasks. So it can be a robot, like a robot arm, industrial robot, or a cobot. It can be a very specialized robot on the top right. You see a harvesting robot, or actually it's a leaf cutting robot, which is a mobile platform with a robotic device on top. On the bottom left is also an AMR, which is like a standard AGV, but also with a standard robot or cobot arm mounted on top. And there's a single controller controlling all the access in this application. And bottom right is a project we did for DLR, the German Aerospace Agency. It's a fiber laying robot, but that also fits in our application, in our standard application. So we can configure it for very strange things already. So that means that 80% of the applications that our clients have are already covered by this single app that we developed over the time. But yes, 80% is maybe not good enough for you. You want to have 100% of your customer satisfaction. So you also need to implement these last 20%. And there we have something that we can actually provide you with a template of this application. So you get the complete structure, like the framework of your house, and everything already works. And then you can take it apart partially. You don't have to break it down completely, but you can just replace the middle part. Maybe you have some really strange kinematics with 20 wheels, and then you have the freedom to actually replace the middle part that needs replacement, but keep all the other parts. And if you go one step further, then later you can also replace all the color parts with your own parts as well. So this is what we mean by providing you the freedom to do whatever you want. But we can do it much faster if we do it this way. So this is a typical timeline of how a project works. So our clients are OEMs. They build mobile robots or other kinds of machines. And they start with, on the software side, with an app. And they don't even have any hardware yet. So they just have a concept, an idea. Maybe they have a 3D model. And with this app, we can deploy it to maybe a virtual machine running in the cloud. And with that also comes a simulation of the machine. So you can also configure simulated AGV, exactly the way how it looks in your case, with how many wheels you like. This visualization is also linked to a dynamic model, so it actually replicates the complete behavior of the electronics and the mechanics down to the CAD level. So the software actually doesn't know the difference if there is real hardware or fake hardware. And with this, you can already go to your clients and show them the concept that you came up with for them. And then later, when, let's say, 80% of this proof of concept this is already functioning, you can connect hardware, you can make it work, and later comes, if you are missing these 20% that we don't provide in the standard app, we can fix this in this template. So we do a little bit of customization for you, but in our cases, the projects that we have done, also for this agricultural robot, for instance, the software is always finished earlier than the hardware. So we actually do the acceptance with the virtual hardware, so with the model, with our client, and then we wait until all the parts have arrived and the machine is assembled, and then the client does its acceptance with the real hardware. After that, we also can provide updates, of course, to the software, like a proper software company. And here you see then one of the projects that we did. This is for a company called Priva. It's a leaf cutting robot, and it was also completely modular. Although it looks like a product, this is a completely modular design. So now this company is actually putting a different top on the same base. So the driving platform is exactly the same, but we can reconfigure the software that different robot kinematics also works with the same application. Okay, so we like to give this advice to our clients that think whatever is possible. So whatever requirements you come up with, think that it's possible to implement this, and the platform should not be the limiting factor. There's now enough technology that you can mix all these different domains as long as you have the expertise to think about it. And as a little bit of a cherry of the cake, we have now been talking about mobile robots. I'm going to show you one very exciting project that we did last year. This is also a mobile robot, but it's a flying mobile robot. So we did a project for a company in the US where we converted manned aircraft with motor cortex. It was not this app because it's kind of really special. So we built a new application. We use used EtherCAT to drive actuators that actually take control of the aircraft. So it was a flight control system. We also removed the propeller of this aircraft and connected the towing hook via a force sensor. Actually, this aircraft was being towed behind a tractor aircraft. And the idea is that you solve logistic problems by making trains in the sky. So you have one tractor aircraft and then many more aircraft being towed behind it. And when they reach their destination, the towed aircraft, they kind of land autonomously at the airport. And here you see Ruben in the airplane with his tablet, where he's actually using motor cortex to control the aircraft, and there's also camera view outside, how we can autonomously track the tractor aircraft. So this is also possible with our platform. Okay, I also want to invite you to, it's very hard to read, but if you Google for Motor Cortex, which is our product name, or Vexually, which is our company name, you can find also our Vimeo channel, which is where a lot of videos of our kind of projects get viewed, and maybe it can inspire you to create new ideas. Thank you. Maybe you have some questions. Any questions?
So you also deal with localization and navigation, you mentioned that at the beginning, or is it only like motor control?
No, we don't do localization and we don't do navigation. So motion control, that is our main subject. But we interface, of course, with local navigation systems.
So that comes from your clients then? Like
yeah, partners. So we partner with companies that provide this kind of technology and then provide this clear interface. How you can send us either velocity commands or like a trajectory, and we play the trajectory on the platform. Any other questions? Yeah, we have a little corner in the back where our little booth is. There we have a simulation of the big boy drive system. Thank you very much.
Okay, the next lecture will be in 15 minutes. We will be hearing Dr. Alexander Blass from Mobile Robotics. He will tell us something about cognitive skills and integrated safety, enabling new apps for AMRs. Yeah. Sorry for störung.
Ja.
Hello, 1, 2, 3. Hello, 1, 2, 3. I can hear you fine. It's good. Yeah. Yeah, sure. 1, 2, 3. Testing. 1, 2, 3. A little bit louder. I believe it's fine. No? If I speak closer, it will sound a little louder. Yeah. Yes. 1, 2, 3, testing. 1, 2, 3. 1, 2, 3, testing. 1, 2, 3. 1, 2, 3, testing. 1, 2, 3. It's awesome. It sounds really well.
Which ones were you?
Some of these large language models are some solutions.
¿Apagado? ¿Ahora qué tal? Sí, sí, escuchando. Escutami da verdade.
Just, wow. Now it's loud. That's good. So next presentation is about to start. We are going to listen to Dr. Alexander Blas from Mobile Robotics. He will tell us something about the cognitive skills.
Yes, hello everyone. I promise it's going to be very interesting. So also the gentleman in the back, it's not going to hurt. So please come closer. Yes, hello from my side, hello from Mobile Robotics. I'd like to talk a bit about cognitive robotics, which also involves our AMRs as well, and what are cognitive features. What is neurobotics doing? Because we are a company from Metzingen, which is close by, but whenever I also ask someone on the road, usually in Baden-Württemberg, not many people on the road would say, hey, we have a robotics OEM close by. Internationally, luckily, it's a bit different because the land and also neuro seems to be more and more gaining interest from all sides. I'll start with a quick video. I hope the sound is okay. Let's try.
We are here to create the future. We are here to create the future, a good future, where our technologies assist humans.
My great vision is making robots being an accessory for every human, in every home, in everyday's lives. Are you ready?
Are you?
All the last big things, they were actually created by need.
Our aim is to bring our technology together with their solutions to create even better solutions for mankind.
The goal of Neura is what the company brings to the world, the impact. Being more like a technology provider, platform provider for every company in the world one day. Just giving the next step to advance humanity is, I think, one of the biggest goals.
Yes, to understand what we're doing, the video says it a bit at the end. Our slogan, we serve humanity. The idea is to get robots anywhere and everywhere, so to say. robots that everywhere can be used in any scenario, not only, which is more relevant here, the industrial sector, so to say, but also later on the social sustainability side, so elderly care, but also the consumer market, so household robots. These are the topics we're talking about. We are now on 11 locations, just recently opened number 11 in Munich. You can say quite a bunch, and this is not necessarily because we want to be everywhere, but especially in Baden-Württemberg, we are on 8 locations because strong growth requires to take on locations where we find them, but we're also working again on getting less locations, so to say, and improve on strengthening the location in Metzingen. About 186 as of today employees at Neura. I feel like every time I bring this slide, this number is old again because it's quite a strong growth, which we are very thankful about. And as you saw in the social media, maybe recently also putting more and more effort on increasing our production sites here in Metzingen, pulling stuff away from the Asian market and focusing more and more on not only designed and engineered in Germany, but also produced, so therefore made in Germany. As I said, robots for different kinds of markets, and also robots that can be used by everyone. What does that mean? Of course, nowadays you have some kind of industrial robot, or also some kind of other kind of robot, and usually you need a robotics expert to program these robots. Spend some time, a week or two, to integrate the scenario, and at the end, 99% of the world are not robot experts, and they should also be able to use the robots. So there must be different ways of doing so. And everyone has their own best way of interacting with the robot. Some people talk with the robot, some people want to show the robot something, want to guide the robot. Some people might want to code, and all these things are fine and well, but the robot should be agile enough to allow all of these things for really everyone to be able to use the robot in the way they're most comfortable. There's industrial robots, there's cobots, there's automation in general. If you want to weld 1 million times on a certain spot, you take an industrial robot. That's really fine. That's not what we want to go against. But if you go a step further, then you have cobots. Since a while ago, 2005, I think the market came up. Cobot, collaborative robot, suggests the idea that you can really collaborate with the human. But can you really? Cobot moves until it hits something. The moment it hits something, it has to assume it's a human being, so it has to move very slow, or you have to put a fence around anyways. And so if you look at applications nowadays with cobots, most of them are in an industrial setup anyways, with some fence around. And what that means is a very slow and not so precise and not so good cobot is now in a fence like it would be an industrial robot anyway. So the advantages from a cobot usually can't play out, and instead it's just pushed into an application where it might not be fitting very good. And if you see, there's many of these coming out. I feel like every month there's a new robot supplier that says, hey, I have a robot arm that solves the world's problems. All of them grab components, some motor somewhere, some controller somewhere, and so on. And at the end, a cobot cannot do anything. You need to put a lot of effort around it. We say about 30% of the value of the application, or of the cost of the application, is the cobot itself. You have all the external sensors you need to put around, and effectors, some software, and some safety, of course, at the end to make the whole thing safe. And the moment you change something in the environment, we have experts here that can talk about that in detail, you have to redo all the safety. So at the end, you put all the surrounding in a way that the cobot feels comfortable, so to say. But what comes with the problem then? Because you create an environment and you tell the cobot exactly do this, do this, do this. And then the cobot will do. Have some pick and place application, sure, the cobot will do. But coming back to the setting that I said, we want assistance to the human. To really assist the human, I cannot say do exactly this, 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 because then I usually do it myself much faster, much better. I need to be able to give the whole task I want to be done to the robot and not worry about how it is done. I want to say, I don't care, solve this problem for me, and please also learn from your mistakes so that you don't make the same mistakes again. You need to be able, as a robotic assistant, to autonomously solve problems, because I, as a human, don't care. To do so, the robot needs to be able to detect humans, not only walls, columns, and some AGVs driving around. Because if I assist a human, I need to know that is a human. Comes with also an acceptance point, because if I imagine a robot that calculates the most logic way to move. So if I'm standing next to the robot, and the robot now decides to move super close to me with super high speed and maybe a knife in its hand, so the safety people have to close their eyes anyways for that. But then I might not feel as comfortable, and I don't care about if that is the best way to do for the robot. I won't use it. If I don't feel comfortable with the robot doing something, if I feel scared or something, I won't use it. I won't accept it as an assistant. So it needs to know, here's a human, I have to react different. I have to really accept it's a human to work together. For that, I need some sensors, and I don't need external sensors. There, camera, changes lighting, again, different camera, again, changes the setup. I need, like the human also has, sensors on the same spot. Eyes always at the same spot, ears are the same spot. Similar also to the smartphone, like this gentleman is using right here. You always have some blocks that you can relate to, and if you want to write a new application, you know you can use the camera, you can use some other sensors, you know you have a reliable setup that you can use and don't have to improvise every time you want to do an application again. At the end, if I think, do I buy a robot or do I buy a sports car? The robot will lose time in my mind. Maybe I'm different than you guys, but I think it's quite a common problem. If a robot costs, I don't know, 50, 60, 70,000, I won't have it at home because I'm not a rich Arabian guy that has a lot of money to play with. In industrial setup, it's different because if the return of investors there after a year or two, we don't care what the costs are because it makes sense. But at home, it's different. And therefore, we need to go in a price range where we say robot or e-bike or maybe robot or coffee machine. And suddenly, 5,000, 6,000 euros like this, we are in a range where we think, do we want a robotic assistant at home? If it's useful, why not? That's the difference between a cobot and a cognitive robot. We have it here, the cobot from before. Cobot, part of a small application. We have to put all kinds of stuff around it. We need to create an environment where the cobot is happy to be, so to say. And instead, what we want is a robot that has all of that included and can react to the environment. So I don't have to set everything up and change everything the moment it changes. I have to reset up everything. Instead, I have a robot that I plug in. It works. It has different skills, different applications. Doesn't matter what I need. I will find what I need, or otherwise I create it, like on the smartphone app, and then I just use it. Is that new for us? No. It's what the human does as well in a way. We understand the environment because we have some kind of sensors, eyes, ears, field of touch. We use our brain. We interact with the world, and then some of us also learn from it. And that's what we have in our robots as well. But that's only, like, from a hardware and emotion part, it's only half of it. That is why I always like to show this picture as well. And I have some people know it, nice picture of our CEO, David, who looks like this as well. Here it is. He always points out that it's not about him, about the product, right? Because if we compare a cognitive robot to a smartphone, there's quite some similarity, right? A smartphone is also a mobile phone or a telephone. You can call, but it can do so much more because it's a platform. And the same counts for the cognitive robot. Because I have all the sensors involved, because I have a platform that many people can use for different cases, we have a system that can do whatever it needs to do. Yeah? For example, we have a cobot, or a cognitive robot in this case, we have taught him how to weld. Because there's lack of skilled workers, I don't want to know how to weld, I want the robot how to know. So we work together with a welding expert that teaches the robot how you weld, depending on what seam, what speed, what angle, what material, these kind of things. Now the robot has an application and it knows how to weld. Now the next customer comes. Doesn't need to start from zero. It can use this application and then their robot can also do so. So we have this platform thought that can increase because at the end, if you think about Samsung or Apple on a smartphone, would the App Store be as big if they would be the only ones to write applications? No. It profits from that everyone now can put knowledge into the system and profit by themselves as well. And this is how the whole App Store, the whole platform thought really brings in all the knowledge and brings many, many more skills to the robot. And that's the thought behind our Neuraverse, so to say. There's quite some portfolio, and many people usually think, oh, the company, by the way, next month we get 5 years old. Quite some products for such a young company, and I understand that thought process, but I can promise there is some thought behind our products. We have a cobot, because at the end we need to make revenue, also in industry, and we have the Lara series, which is basically a better, faster, German style, right? Spaltmaß, very important. Better, faster, and cooler cobot that we have in different sizes. Then we have the Myra, our cognitive robot, the world's first and only cognitive robot. And we also have AGVs, and this is the reason why you guys are here, and I'm kind of ignoring to this point, because I want you to understand the cognitive features behind that. At the end, it doesn't matter what product you have. The cognitive features are an add-on, because at the end it's robot agnostic. So also, if you have an AGV from our side, and you have camera involved, or even the combination of AGV and robot arm, you have cognitive features that allow you to go this one step further than was done before. With the AI and the common sense that the robot can bring, you can automate much more than before, because the one thought of, is this really right, or should I change slowly or slightly my application? Huge impact. I usually have a slide here from an automotive OEM, a big one. You know some of these as well. And they had the problem that they have a big box of metal parts, and they could not automate it because it's not a pick out of a box. Pick out of a box and put the piece on. And if the piece is grabbed just slightly wrong, then it's not optimized anymore because it will fall down. So with the cognitive features, they can actually grab and look at what you're grabbing, and then correct slightly. Just a small move, but it makes a strong impact on the optimization of the application. And that's what our Myra stands for, and I usually have next to it the safest, fastest, and smartest cobot, and also the most precise robot there is, because our Myra can go up to 6 micron precision, which is the 10th of a human hair, if you need it. And the way to do so is not just like Silicon Valley style, oh, we only have a good software. You need to have a good system. And so all of these components are part of our in-house IP. You need a good hardware, you need a good software, and you need a good AI as well to combine all of these things to really produce a product, a platform. And so the task of the robot here was to empty stuff from the big box to the small boxes. That was it. And now you can see what it does is something else. Looks weird, but what it does is it sees the other box is full, so it needs to find a solution to fulfill its original task of moving stuff from the big box to the small box. And so before it does that, it empties the other box so that it can move stuff into it. That comes back to this autonomous acting. I give it a task because I don't care what it does with the small boxes before, and I just want this big box to be into the small box. And so it reacts by finding other ways to solve that what was not be able to done before. And the big problem on this is it's not so easy to calculate. It looks quite easy, by the way. Gray on gray is also not so easy. The AI needs to be able to spend time on calculating and thinking. And this robot is not connected to the internet, because if you take a robot and you go to some well-known big companies in Baden-Württemberg and you say, now I'm sending super sensitive data, pictures, video into the cloud, then you go home, because in Germany at least it's not so good. So therefore the AI needs to be able to calculate independent of the internet, and so it's not connected to the internet, so it needs to be very good at selecting data, because not all data is gold, only golden data is gold, some wise person once said. So it needs to be able to focus on the topic, like I focus now on you. I don't care if in the back is other people or other booths. I have the task to talk to you, and so I disconnect everything else. And the robot does the same. The robot understands the task, gets away of all the other data, and therefore can focus on what it needs to do, and does that as well as possible. Also, for example, real-life learning. So the robot gets shown an unknown situation, And the robot now, real life, needs to understand, okay, I cannot put the red cube first in the air and then put the others underneath. I need to start with the green or the yellow and then put the red one on top. So giving it a task, not giving it a solution, because I don't say to the robot, take the green piece, take the yellow piece, take the red piece. I say to the robot, I want this built. And then the robot finds an own way to do so while calculating and real life deciding, this is the task. I don't care about any other sense I get in. I want to focus on this and I'll solve it. On the AI part, of course, the AI will try its best to not punch anyone in the face, so to say, to not hurt. But there's a step further. We talked about collaboration at the beginning, and true collaboration means that not a cobot that is called collaborative gets into a fence and then somehow does something. That's no collaboration with the human. Collaboration is when the robot knows there's a human. Oh, sorry about that. Is that now working? Yes. When the robot knows there's a human and now decides I have to go slower, I have to find another way around, and therefore we have a sensor. It's here as a standalone sensor, you will see in a moment, but it's also possible in the robot flange itself, which can detect safely, that means diverse and redundant, but also privacy protecting, because whenever you use cameras, it's machine learning, so it's not 100% safe, and that's a problem. It's not camera involved, it's two other sensors. One of them is radar based. And you see when the person walks closer, the robot stops. First goes slower, then goes stops. And you see even if you put a shirt on top, doesn't matter. The robot understands what's happening and therefore stops or finds another way around. And so for this sensor now, you really have the chance to allow the robot the interaction with the human. So the robot knows it's a human and not only there's something I don't care too much about. So now that it's over, I smartly now talk about the AGV so no one can stop me, because that's the main topic on it. No, jokes aside. So we have our AGV, which can carry 1 to 5 tons. It's originally made for automotive because you can put the whole car on it. And then instead of having a bit conveyor belt of for example, our Myra, and then if you have a combination of an AGV and a robot arm, you have the ability to autonomously drive around, unload, load stuff, and also provide